Now we're going to review the answers to the practice problems for the first set. So here was the first problem. It was the program we've been looking at before, which was f equals g of h, g plus h minus I plus j. And I gave you the code here, and we're going to walk through it and see how it works. So the first thing that happens in this program is we start out instruction 0. We load instruction 0 into the instruction register. This then tells the control what to do. Control tells the ALU to add, and we go and get our source registers. So we're going to get registers 4 and 5. We're going to do the add. The addition of 2 and 3 is going to be 5. And we store 5 back into our destination register, which is R1. Then we increment the program counter and we go on to the next instruction. Now we're at instruction 4. We're going to load instruction 4 into the instruction register. The control is going to tell the ALU to do an add again. We're going to get the source registers, which in this case are going to be 6 and 7. So we're going to add 1 plus 4. And we're going to write the results now into register 2. So now we've written 5 into registers 1 and 2. Now we increment our program counter. We go on to instruction 8. Instruction 8 is subtract. Now for the subtract, we're going to tell the ALU to do a subtraction. It's going to get its sources, which is R1 and R2. We're going to do the subtraction. We're subtracting 5 from 5, which is going to give us 0, and we're storing the results into R3. And so here are the results after this. The first two instructions added 2 and 3 and 1 and 4 respectively and stored them in R1 and R2. And then the last instruction subtracted 5 from R1 and R2 and stored it in R3. The next question was about unaligned accesses, and it asked how you would load the data word starting at address 5. Here's a view of our memory, and if we look at address starting at address 5, here's the data we want to load. We want to load a word that has B, C, D, and E in it. Now the way to do this is we're going to have to do two loads. So the first load, we're going to load address 4. So this is going to load starting at this address, and it's going to load the full word. So this time it's going to load A, B, C, D, when what we really want is B, C, D, E. So we've loaded this part of the data, which is most of the data we want, but not all of it. So the first thing we're going to do here is we're going to shift it left by 1 byte. So shift left logical. We've loaded into R3, so we're going to shift R3 to the left, shift it 8 bits or 1 byte. So the result of this is going to be as you see here. We've now got B, C, D, and 0. We've shifted everything to the left by 1. Now we can go and load that last piece of data that we're missing. So we can do load byte. And we can tell it to load the byte at address 8. This is going to load just the E that we saw there. So it's going to load this E, and it's going to fill the rest of the word with zeros. So this is what we get from that load. We get 000E, and this is now stored in R4. Now what we need to do is we need to combine these. We need to combine this word, which is an R3, which has a 0 here, with this word here, which is an R4, which has zeros here. And to combine them, we're going to use an OR. And the OR will replace the contents of this 0 with E, and replace the contents of these zeros with the B, C, and D. So we go ahead and do our OR. When we OR them, we now get our final results. So in order to do the unaligned access, we had to do 4 instructions. We had to first load the first word, then we had to shift it, then we had to load the byte from the last word, and then we had to OR them together. So the third question was about doing data transfers. So here we're going to load data pointed to a variable, pointed to by a register. So if we walk through this program, we start at instruction 0. When we're going to do this instruction here, add immediate R5, R0, 24. Now R0 is always 0, so what this instruction does is it puts 24 into R5. So if we look at the control, we're going to do an add. We're going to add 0 and 24. We're going to store it into R5. So now we've got 24 in R5. This is then going to be the address of the variable we want to change in memory. So if you look at our memory over here, here's our variable A, and it has address 24. And we just stored 24 into our register file. Now we increment the program counter. We go on to the next program. In this case, it's another add immediate with an R0 and 512. So this is going to store 512 into R6. So if we look at how this works, we've got an add. We're going to add 0 plus 512 and store the results into R6. So now we've got 512 in R6. Now we're going to increment the program counter and go on to our store word instruction. So the store word instruction here is going to store the word that's at the value in R6 into the location pointed to R5 plus 0. So what this is going to do is it's going to use the ALU to do an add to generate the address. So we're going to add the value from 24 and 0, which is going to give us 24, and store that in the memory address register. This is going to be used to give us the address for which part of the memory we want to access. Then we're going to take the value from R6 and put this in the data register. This is the data that we're going to send to the memory. We then send this data to the memory. It updates the data in the memory at the location pointed to by the address, and we have the final results. We've now stored the value 512 in the address 24. The next question was about needing to do simultaneous accesses to the register file. So you have 4 instructions here, and the question is how many reads and writes does each instruction need? So for the first instruction, we have 1 write, this is we're going to write the results, 1 read, we're going to use the value from R5, and we have a constant. The constant, remember, comes from the immediate field in the instruction. So for this instruction, we have a 1 write, 1 read, and some data from the instruction. For the subtract here, we're going to write to R4, and we're going to read from R5 and R12. Remember, we're subtracting R5 and R12 and storing the results in R4. So for this instruction, we're doing 1 write and 2 reads. For the branch, we're going to read R3 and we're going to read R0 because we need to compare them, and we're going to read the address of the loop to branch to, but this is from the immediate field in the instruction. So for this instruction, we're going to read 2 values and we're going to read an immediate field from the instruction. Finally, for the jump done, all we need here is the immediate field from the instruction. So we don't need to read and write any registers. Now the second question here was, what is the minimum number of reads and writes we need? Well, if we look at these instructions here, we see that instruction 2, the subtraction, needs to be able to do 2 reads and 1 write at the same time. And that's the minimum value. So to make a register file work with MIPS ISA, we need to have a register file that can read 2 values and write 1 value at the same time. The last instruction was about branching. So how do we actually implement this C code in MIPS assembly? And the trick to this question was there's no instruction which says compare if b minus 7 equals a. So we're first going to have to do b minus 7 and then compare if it equals to a. So let's take a look at that. So the first instruction here is going to be a subtract immediate, and I'm going to subtract R5 and 7. So now if R5 is b, so I'm storing b minus 7 into a temporary register, R2. Now I'm going to do my branch not equals, and I'm going to compare R4 and R2. This is saying if a does not equal b minus 7, then I'm going to jump to skip. Now if a did equal b minus 7, I want to do the addition. So here's the addition, add immediate, R4, R4, 2. This is going to do a equals a plus 2. And then if I didn't want to do that, here's my label for skip, where I'll jump over if I'm going to skip that part, and then I continue on with my code.